Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good evening, ladies and gentlemen. I will present my research about experimental and numerical investigation of a low temperature PEM fuel cell with different fuel flow rate to improve fuel cell performance. In the International Conference on Energy Storage Technology and Application, I and my friend research team. My name is Yusuf Diwantara Lambang, Kurnia Ningsih, Anis Royatin, Bapak Prasetyo, Fatul Arifin, and my student helped me to research in this study. This is my research. Proton exchange membrane fuel cell serve as a separator to prevent reactant hydrogen and oxygen from mixing in the cell channel, then transfer proton from the anode side to the cathode side. This is my research about fuel cell. This background from fuel cell I find from some research from Singh et al., Cooper and Zhang in 2018 state that a microscale fuel cell system can be applied by utilizing laminar flow characteristics with a low Reynolds number. And the other researcher from Zhang et al., Zhang et al., and we use also the Butterformer kinetic reaction equation expresses the rates of the electrochemical reaction of oxidation and reduction. This some research before, and I will research entitled experimental and numerical investigation of a low temperature proton exchange membrane fuel cell with different fuel flow rate to improve fuel cell performance. This is my objective in the research: to design, simulate, study, and obtain the best characteristics of fuel cell with different conditions. This is the material and method. The first, the computation domain and geometry. My fuel cell at volumetric flow rate, we can variation 6 milliliter per minute, 12, 18, and 24, also 30 milliliter per minute PEM fuel cell with 20 millimeter long, 1 meter wide, and 1 meter height cell channel was numerically examined. This is a geometry PEM fuel cell with a flow channel and boundaries of the computational domain. The material method, we use isothermal domain. Electrode are regarded as an isotropic, porous, and homogeneous medium. Riemann equation, and also to get VIP curve and electroreaction for the fuel cell. This is we use some equation to get the characteristic of fuel cell. This is use Brinkman equation to get the porosity in the permeability of the porous media in the fuel cell. And so this is a parameter simulation. We use some parameter like that. This is method. We use flowchart for algorithm for the current power in my fuel cell. The first, we use structural model design, input cell potential to analyze the local current densities, and then fit model, validated model, and we get convergent momentum energy mass fraction potential for current density. If not convergent, we use to reply this project. But if the convergent in the program, we can display activation upper potential, local cell current density, and cell power densities. This is wiring diagram. We use my fuel cell. In the fuel cell have power supply, push width modulator to 4 meter ampere meter, hydrogen generator. We use dry electrolyzer, and this is a fuel cell to related 4 meter and ampere meter in the system fuel cell. Result and design. This is a product my fuel cell, a hydrogen generator dry type. This is and this is a fuel cell model. Have power supply, hydrogen generator, stack fuel cell, PEM module, control unit, DC-AC inverter module, reservoir tank, battery, DC 4 meter, AC 4 meter, power switch, and PEM switch in this product fuel cell. Small scale fuel cell for power plant. And this is theoritis. The result of my research polarization curve for 50 mole per meter cubic with polymetallic flow rate 6 milliliter per minute, 12, 18, 2000 to 24, and 30 milliliter per minute. And this is like this for concentration for 50 mole per meter cubic. This is voltage and current curve, and this is power density and current electric current curve. This is the simulation modeling for the anode hydrogen concentration and cathode hydrogen concentration, and the result discussion for this is membrane current density modeling, and this is for simulation modeling velocity of the flow rate and channel velocity flow in the cathode channel. This is for characteristics of a cell output current with different voltage and hydrogen gas discharge. And this is characteristic for fuel cell output current and output power. When output current of the fuel cell increase, the output power of the fuel cell also increase. This is in the characteristic for my fuel cell. Also, this is efficiency with different hydrogen voltage flow rate. We use 1, 2, 3, 4, 5, 6 parameters variation for flow rate. And also, this is characteristic of hydrogen discharge and fuel cell efficiency and output power. The increasing hydrogen discharge entering the fuel cell will increase the output power produced by the fuel cell. So this is efficiency, voltage flow rate, and electric power. And also this is a specific fuel consumption as FC in my fuel cell with different voltage flow rate. And the conclusion in my research, the highest amount of hydrogen gas discharge produced by the hydrogen generator is 40 meter per minute at concentration 1.5 molar. Yeah. KOH solution with an input current of 20 ampere. The higher the current and concentration of solution, the higher the amount of gas production. What you say? The second, the operating voltage of the fuel cell is 2.34 until 34. The base supply hydrogen discharge is 33 milliliter per minute with cell current and voltage are 175 milliampere and 2.24 respectively. And finally, this conclusion, the highest efficiency in the hydrogen generator is 85%, and the highest efficiency is the fuel cell at 4.58% at SFC 0.654 kilogram per kilowatt hour. This is my presentation, and for the attention, thank you very much.